Okay, welcome to Robotics 1. In last class, this is what we reviewed. We looked at the forward kinematics, we looked at the unit vector transformation, and finally, we talked about the, the coordinate transformation. Now, what I want to do is, in today's class, I would like to review the most important coordinate transformation that we are going to use. There are three coordinate transformations: rotation about x, rotation about y, and rotation about z. But if you look at our sign convention, our rotary joints, the axes will coincide with the z axis of the coordinate system. So the most important coordinate transformation that we should be remembering is the rotation about z. And I would review it once again, and then I will show you how to solve coordinate transformation problems. So this is lecture 3. So what we have is we have this coordinate system. This is x naught. This is y naught. And this coordinate system is rotated to x1 and y1. And z is coming out. So z is something like this. So this is z1 and this is z0. So the rotation is a positive rotation theta z. And I want to relate the coordinate systems x naught, y naught, z naught with the coordinate system x1, y1, z1. Please understand, x naught, y naught, z naught is the 0th frame. And x1, y1, z1 is the first frame. So the rotation transformation that relates 0th frame to the first frame is given as 0R1. So this is the initial frame, or I call it the old frame, and this is called as the new frame. Also, this can be considered as from to. So we are going from old frame to the new frame. And does anyone remember the coordinate transformation matrix? The coordinate transformation matrix, the new frame will be here, old frame will be here, and this is super simple: cosine theta z minus sine theta z, sine theta z, cosine theta z, 0, 0, 0, 0, 1. Are you with me so far? In other words, this can also be written as, if you recollect, we derived this something like, you have this, the old coordinate vector. This is the transformation, and this is the new coordinate vector. Now the idea is, what we want to do is, we want to take this transformation, which is called as 0R1, and make it part of something called as the homogeneous transformation. Now, this concept is super duper important. And if you read any textbook, it's very confusing, but it should not be that confusing. So understand what is a homogeneous transformation. This matrix is a 3 by 3 matrix. homogeneous transformation 0H1 is a 4x4 transformation. This is a 4x4 transformation. And this 4x4 transformation matrix, it's split something like this. So you have the first 3x3 transformation, which is over here. So this is the 3x3 transformation, which is over here, 0, R1. All the rows in the last, all the columns in the last row, the first three are 0. This number is going to be 1. And this is the most important part. There are these 3 blanks. 1, 2, 3. And these 3, and I will repeat this again and again and again, but I want you to understand this. This is location of frame 1 with respect to frame 0. And here is the most important part. In frame 0 coordinate. And I will take examples and show you what that means. I'm not going to derive homogeneous transformations the way that are derived in robotics textbooks. But what I'm going to say is homogeneous transformation is a 4x4 matrix that includes the rotation information between the frames and the translation information between the frames. So in this particular case, please understand there is no translation. Frame 0 and frame 1 are on top of each other. But if you have a robot joint, most unlikely these frames will be on top of each other. They will be rotating and they will have some type of translation. So the homogeneous transformation matrix will take care of the rotation and translation between the frames. Everyone understood this? Now this translation is super critical because if you have translation, right now we have a choice. That translation can be expressed in the first frame or the translation can be expressed in the 0th frame because these are 2 different coordinate systems. Right now they are like coinciding, but they could be apart. So which frame should we use? Always remember, in homogeneous transformation matrix, the translation information is coded with respect to the previous frame, not the current frame, previous frame. Everyone understood this? So now if I want a homogeneous transformation, which is between 1H2, then my rotation matrix is going to be 1R2. I'm going from frame 1, I'm going to go to 2, and my translation information will be with respect to frame 1, but not frame 2. Everyone understood this? Next thing which I want to talk about, and in the first problem, it won't be needed, but I just want to tell you something else, is imagine that you can have successive rotations. So for an example, I can express 0R2 is equal to 0R1 multiplied by 1R2. You can see this guy gets cancelled, and finally I have 0R2. Similarly, 0H2 can be written as 0H1 multiplied by 1H2 is equal to 0H2. So you can multiply those sequentially. Important note about the rotation matrices. Rotation matrices are orthonormal matrices, which means the inverse of the rotation matrix 0 R1 inverse is equal to the transpose of the rotation matrix. So rotate, and the determinant of rotation matrix is identity matrix. Everyone understood this? So actually it's 1. Determinant is a scalar quantity, so I should say 1. So everyone understood? Yeah.
So when you say 0 or 2, it means the position of
From
the second frame with respect to the 0th frame.
correct. So I'm going from 0th frame to second frame.
So basically, some point in second frame with respect to the same point with respect to the 0th frame.
Yes, and bear with me for a second. I would show it to you with an example. Remember the same example that we talked about in last class? But only thing is, I'm gonna try to solve this with the technique of homogeneous transformation. And some of you may say I'm wasting time, and you're right. For this simple problem, this homogeneous transformation technique is really not needed. But please understand, this technique will work for any spatial mechanism. Let me understand. This technique will work for any spatial mechanism. As soon as you have a mechanism, every mechanism will comprise of joints and links. Joints and links. As soon as you decompose that spatial mechanism, a three-dimensional mechanism, into the joints, rotary, prismatic, or spherical, if you have a joint and link, as soon as you separate those, the homogeneous transformation technique will allow you to solve any forward kinematics problem. So, and in case if you are wondering what is this, remember this is the same problem that we tried to solve in last class. So basically we have a link, and then we have another joint. Now think about it like I have a motor here, I have a motor here, and then basically what I have is I have another link over here. And if you add a prismatic joint over here, it becomes your SCARA robot. So this is motor, this is motor. So right now, think about this, that this is your first joint, this is your second joint, and this is called as the kinematic diagram. Kinematic diagram is always drawn. Yeah.
Can you start with any of the joints being the first joint?
No, you have to start with the joint, which is the inertial, attached to the inertial frame.
Oh, I see.
You have to start with the joint, which is attached to the inertial frame. So inertial frame is the fixed frame. So now let me start. So this is going to be my frame 0. And this zeroth frame is fixed frame. Remember the rules that we talked about in last class? Rule number 1, Z through joint axis. Then second, xn must intersect Zn and Zn minus 1. And the last rule is RHS coordinate system. Are you with me so far? These are the rules that we talked about. When we study DH parameter, we'll split one of these rules and we'll make it into the 4 rules that are the same rules that are used for DH parameter. The first frame must be fixed frame. This is also called as the inertial frame or Newtonian frame. And this is going to be my Z0. This is going to be my X0. Curl your fingers. X, Y, Z is going out. I mean, sorry, X, Z, Y is going out. This is what exactly we did in last class. Remember? Same thing here. This is Z1. I'm going to have X1. And this is going to be my Y1. Are you with me so far? For the last point, which is also called as the end effector, there is not a single joint. There is not a prismatic joint or there is not a revolute joint. So I am free to choose the frame I want to be. So, but it's easier to consider the frame which is aligned with the previous frame. So X2, Z2, Y2. Are you with me so far? Now I'm going to assign the link lengths. So this is a physical link. So I'm going to call this maybe A1. I'm going to call this A2. I'm going to call this A3. And I'm going to call this A4. So please note, in this particular case, these links are fixed because if you look at the physics of the problem, this length is A1. This length is A2. This length is A3. And this length is A4. Are you with me so far? So you have a kinematic diagram, which is the simplest representation of that actual robot. Now what I want to do is, this is the procedure that I want to follow. So I want to find out the rotations about joint 1. So I'm going to call this theta 1. I'm going to call this theta 2. And some of you may ask me about this convention is, why am I choosing theta 1? Why not theta 0? Why am I choosing theta 2? Why not theta 1? This is the same convention that is used in the robotics books. And the reason I want to use this convention is because I want you to verify that if you look at the complicated problems solved using the DH parameters, and if you solve the problems using the technique that we are discussing here, at the end, you'll get the exact same answer. But the biggest part is the technique which I'm going to discuss here can be coded inside the Matlab very easily. I mean, DH parameters can also be coded properly, but not now. Towards the end of this, maybe next 2 or 3 classes, I will show you the cases where the DH parameter technique fails. And then you have to use something called as the modified DH parameter to overcome those problems. But this technique will always work. Okay. Now what I'm going to do is, so here is what I want to do. I want to, at the end, just to answer the question that was asked. At the end, I want to write down this frame 2 with respect to frame 0. So what I need is 0 H2. Do you agree with me? To find 0 H2, I need 0 H1, and then I want to multiply by 1 H2. Do you agree with me? Now, next, if I want to find 0 H1, I need to find out 0 R1 and corresponding translations. I need to find out 1 R2, 1 R2 and corresponding translations. Everyone understood that? Yeah.
You can't use the order of the.
Nope. Left to right. Order is very important. Yeah.
I have that doubt, like, I don't know, it's very, doubt, but what I've seen that if you are applying one transformation and then other transformation is the same, first we, like, from my side here, I first multiply the second transformation and then the first one to get the total effect of that.
Yes.
But why in that we are.
Yeah, you can use that technique with the technique that I'm discussing and finally decide which techniques make sense or which technique is
No,
easier.
I'm understanding why it's like this side from. Like,
That's just, it's a convention, and convention is for convenience. So I find this convention convenient.
Oh,
So
okay,
that's
okay.
why,
Just okay.
no, so why not DH parameters? I find this technique better. So, but at the end, finally, if your answer is correct, doesn't matter what technique you use. Yeah.
So there that X0, Y0, Z0 is fixed frame.
Yes, it's not rotating. It's fixed.
Okay, so the joint which rotates with respect to the fixed frame, what is that?
So basically, what is happening, and bear with me for a second. So X0, Y0, Z0 is the fixed frame, but this motor or this joint is rotating about Z0. Rotating about Z0.
So should we assign a new frame to that too? So that
Hold your horses. We can add as many frames as we want in between, but why to use unnecessary frames? When there is a need, we'll add a frame. So bear with me for a second. And probably I get this. This is so funny. So I get this all the time. Like, hey, I use something like this, and this is how I solved in my earlier robotics one. That's totally fine. So if you have studied robotics one before or done forward kinematics, DH parameters, and used different conventions, that's totally fine. But there are a lot of students here, to the best of my knowledge, who have not taken any course in coordinate transformation, linear algebra. So I'm going to start with very basic technique, which is like a step-by-step recipe that will get you from point 0 to point 2. And then to the velocity, accelerations, and forces and moments. So, but you are welcome to compare this with the techniques in the textbook. As a matter of fact, if you look at Niku's textbook, this technique is not discussed, or the techniques that you have studied in the past. But bear with me for a second. You will see the power of this technique in just 2 minutes. So now what I'm going to do is I need to find out 0 R1. 0 R1. And as you know, 0 R1, what it is? Cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. Do you agree with me? However, I want to add one more thing to it, and this is super duper important. Now, what I want to do is, in this particular case, it may not be so apparent, but it will be apparent later. So this is called as the projection matrix, and this is very important. This is called as the projection matrix. In this particular case, Z0, X0, and Y0. Z0, X0 in Y0 in kinematic diagram are aligned with x1, y1, z1, but there is no guarantee that x1 will be aligned with x0, y1 would be aligned with y0. We know for the fact that z0 and z1 will be aligned, but there is no guarantee that they will be pointing in the same direction. Do you agree with me? So you can assume z0 going up and z1 going down. Okay, so in this case, the first problem, everything is simple. But check this out. So this is called as the projection matrix. And how do you determine this projection matrix? Same, x1, y1, z1. This takes care of the alignment between the frames. x0, y0, z0. Can you see x1 is in the same direction as x0? Do you agree with me? So this is 1, 0. y1 has no relationship whatsoever with x0. z1 has no relationship with x0. So x1, y1, y0, 0. y1, if you look at y1, is aligned with y0. z1 is aligned with not aligned with y0. So you have 0, 0, 1. Do you agree with me? So this is the alignment or projection matrix, which means my final 0R1 is going to be the product of the rotation matrix multiplied by the projection or alignment matrix. Alignment matrix or the projection matrix is identity. So I'm going to get the same thing. Cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1. Are you with me? This is my final. This is my final 0R1. This is the 0R1 that we have to use when we find 0H1. So 0H1, first, it's going to have a 3x3 matrix. And that 3x3 matrix is going to be 0R1, which is cosine theta 1 minus sine theta 1, 0, sine theta 1, cosine theta 1, 0, 0, 0, 1, 0, 0, 0, and then I have 1. Now comes the important part. I have to take care of translations, and I'm going to go very slow. So this is the translation in X. This is the translation in Y. And this is the translation in Z. So how is it found out? Now, whatever relationship for translation we write, that translation relationship should be the same for all values of theta. Please understand. Theta is the joint variable. So please understand that length is rotating at theta 1. So whatever translation relationship we write, that translation relationship must hold true no matter what my value of theta is. My value of theta is 0 or theta 1 is 0, that relationship should hold true. If my theta is 90 degrees, that should hold true. If my theta is 360 degrees, it should hold true. Now, if you look at the distance, and initially it may take a little bit of time, I want you to look from the top. So look from the top, and you would realize that this is going to be A2 cosine of theta 1. This is going to be A2 sine of theta 1. and the last one is going to be A1. And in case if you are wondering, what I want you to do is, I want you to look from here. If you look from here, what would you observe? And imagine that joint has rotated by some non-zero theta 1. If this joint has rotated by non-zero theta 1, and if you are looking from top, here is what you will see. You will see x0, you will see y0, and this guy, actually this guy is going to be your A2. This is A2, and this will be A2 cosine theta 1, and this guy will be A2 sine theta 1. Same figure, I'm drawing it over here. X0, and please understand, forget frame X1. We have to write down these translations in frame 0. So these translations should be in frame 0, expressed in 0th frame. So if you look at, so just when theta is 0, do you agree with me? This is what is going to be A2. When theta is non-zero, same A2 will be over here. And then you are going to have, this is theta 1. The distance, x distance is going to be A2 cosine theta 1. And this is going to be A2 sine theta 1. Are you with me so far? Now, if you look at the Z is not changing. The distance between these two frames is not changing. And this relationship is always going to be valid, whether theta is 0, theta is 150, 160, 360, 720, whatever it is. Everyone understood this? Yes.
What are the units for everything in the matrix?
So rotation matrix basically comprises of radians or degrees. And the translation will be in millimeters or meters or centimeters. Yes.
How do we use this matrix? Like,
Oh, we are getting there.
we're getting there. Okay, thanks.
Okay, now this is done. Now what we want to do is, I want to repeat the same process. Everyone understood what I did here? Simple, huh? Okay. Now what I want to do is, I want to do 1R2. Can you see 1R2 is again replica of 0R1, except cosine theta 2 minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. But let's not forget the projection matrix. And in this case, projection matrix is x2, y2, z2, x1, y1, z1. So for a couple of problems, I have to go slow. But once I'm done with, I think I will solve about 7 or 8 problems. Once I'm done with all the possible robot cases, you can just look at the robot kinematic diagram and draw the homogeneous transformations. So now again, same logic. Can you see that x2 is aligned with x1? Are you with me? X2 is in the same direction as x1. Y2 is in the same direction as y1. Z2 is in the same direction as Z1. Agreed? So it will be 1, 1, 1. Everyone understood this? Wait. We'll get there step by step. And once you multiply, zero, zero, one. This is your final 1R2 matrix. Are you with me? This is not your final 1R2 matrix. This matrix is not your final matrix. In this particular case, since the projection matrix, I need to write it here. This is called as the projection matrix. Projection matrix. In this particular case, projection matrix is identity. That's why this transformation is same as the final transformation. But it doesn't have to be. And you will realize that once I add a prismatic joint at the end for SCARA, you will get some weird projection matrices. Okay, now next part is 1H2. 1H2, the first part is easy, and I'm gonna just write it down here. Cosine minus sine theta 2, 0, sine theta 2, cosine theta 2, 0, 0, 0, 1. And then this will be always 1 in homogeneous transformation matrix. This will all be zeros. And now I will have the translation terms. Now this translation is between frame 1. So this is my frame 1. And this is my frame 2. This is my frame 0. So translation between frame 2 and frame 1 expressed in frame 1. Once again, translation of frame 2 with respect to frame 1 expressed in frame 1. And can someone tell me what would that be? What would be the translation about x1? It will be a4 cosine theta 2, right? A4 cosine theta 2. What would be the translation about y? It will be a4. And then this will be a3. And now here comes the last part, wherein to find out 0h2, I multiply 0h1 multiply by 1h2. And this is the multiplication of 4 by 4 matrices. Okay. Typically, what we do is, once we derive the homogeneous transformations, we use Matlab to do these multiplications. And all the problems that I'm going to solve, I would use Matlab. But for this first problem, I'm going to perform this 4 by 4 matrix multiplication by hand, just so you know what that process is. And then you'll realize that you will see some terms, cyclic terms emerging based on the configuration of robot. So I'm going to perform this multiplication. And this is going to be a big multiplication. So please bear with me. And there is a possibility that I can make mistakes. So if I make mistakes, please let me know. And usually what I do is, at this point, once the homogeneous transformations are done, we actually code these in Matlab. So let me do the multiplication by hand, and then I will show you how to solve this problem in Matlab. 0, 0, 0, 1, This is gonna be A2 cosine theta 2, A2 sine theta 2, A1 multiplied by cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1, 0, 0, 0, and A4 cosine theta 2. I made a mistake. A4 sine theta 2, and this is A3. So if you look at the matrix multiplication, what you do is you have this first row, multiply this with the first column. First row, first column. So the first term is going to be cosine theta 1, cosine theta 2, minus sine theta 1, sine theta 2. And as you can see, everything else is 0. First row, second column. So this guy, first row, so this is going to be cosine theta 1 minus sine theta 2 minus sine theta 1 cosine theta 2. Everything else is 0. First row, third column. So as you can see, this guy is gonna get 0. And this guy, as you can see, first row, fourth column, this is going to be A4 cosine theta 2 cosine theta 1 minus A4 sine theta 2 sine theta 1. So first row, first column, and then finally, as you can see, the last term will get added plus A2 sine, or A2 cosine. Actually, I should write this properly because otherwise I won't have enough space. So A4 cosine theta 1 minus A4 sine theta 2 theta 1 plus A2 cosine theta 1. Do you agree with me? Now, next product multiplication, sine theta 1 cosine theta 2 cosine theta 1 sine theta 2. Then, yeah, there will be, no, wait a second. There is one more. Sine theta 2 sine theta 1. This will be negative plus cosine theta 1 cosine theta 2. Then there will be 0. Then A4 cosine theta 2 sine theta 1 plus A4 sine theta 2 A4 sine theta 2 cosine theta 1 plus A2 sine theta 1. All right, the hard part is done. Now here, if you see all zeros, 1. Agreed? And the last part is this guy multiplied with this guy. And this is, I will point it out once again. This term multiplied by this term. 0, 0, A3 multiplied by 1 plus 1 multiplied by A1. And 0, 0, 0, 1. Are you with me so far? We have solved forward kinematics problems. So this first part tells me the rotation of frame number 2 with respect to frame number 1, which is 0, R2. So this is all this. This is the translation of frame 2 with respect to frame 0. Are you with me so far? Now I'm going to write this again, and you will realize that, I mean, you should see there is a pattern emerging. I don't know if you have seen this pattern. This pattern is something like A4. I'll write this down, okay? So X, I'm going to call X end effector, which is, if I say this is my end effector, this is my end effector, the X position of end effector in the 0th frame is given as, I want you to observe this, A4 cosine theta 2 cosine theta 1 minus A4 sine theta 2 sine theta 1. This looks to me like A4 cosine of theta 1 plus theta 2. Are you with me? Plus A2 cosine theta 1. Next thing, Y end effector is going to look like A4 cosine theta 2 sine theta 1 sine theta 2 cosine theta 1. What is that? Sine theta 1 plus theta 2 plus A2 sine theta 1. The last part is Y and Z end effector. The end effector is A3 plus A1. And it is very important to note that A3 plus A1 does not have cosine or sine terms because they are vertical, they are fixed. Those distances don't change. Are you with me so far? Now, what is the physical interpretation of this? What does this all mean? So for that, what I want to do is, I would like to repeat, I would like to show this kinematic diagram again and try to give you some insight into what these terms mean. So check this out. This is theta 1. This is theta 2. Do you agree with me? This distance is A1. This distance is A3, right? So you agree with me that if this is my inertial frame, if this is my 0th frame, no matter what I do, the Z distance, let me give you the coordinate frame. And this is the coordinate frame that everything is expressed in. Everything is expressed in inertial coordinate frame. This is Z0, X0, and Y0. So this is the end effector. So end effector Z position, no matter whatever is the value of theta, no matter what the value of theta is always going to be A1 plus A3. Do you agree with me? So yes, this is verified. Now what about X end effector and Y end effector? For that, let's be a little creative. Now what I want you to do is, I want you to look from top. And I want to assume a non-zero Z rotation. So if I were to look at it, you are looking from top. This is what you'll observe. You will see this is X0. This is Y0. This is going to be your first frame. And this is your first link, which is A3. And then this is the second link, which is A4. Are you with me so far? Now, let's write down the joint coordinates. Remember, our joint coordinates or the joint rotations are with respect to the kinematic diagram. What was our kinematic diagram? Both the links flat. Do you agree with me? Both the links flat. Now, the diagram that I have shown here, so kinematic diagram was drawn like this, but the actual position that I'm showing you here is something like this. Do you agree with me? I want you to observe the most important part. My theta 1 is with respect to this horizontal line. Do you agree with me? And my theta 2 is with respect to this horizontal line. Theta 1 and then theta 2. Are you with me? Theta 1, theta 2. Theta 1, theta 2. Everyone understood this? Because this is super duper important for the next argument that I'm going to make. So this is theta 1 and this is theta 2. Are you with me so far? So what I want to do is, this is the end effector. And I want to find out the end effector position from the zeroed coordinate frame. And I'm going to take projections. So this is going to be theta 1. This will be A3 cosine theta 1. And this guy is going to be, can someone guess? A4. Please note, now this total angle is theta 1 plus theta 2. Now the total exposition is nothing but this guy. So this is A2. This is A2. A2 cosine theta 1. So this becomes A2 cosine theta 1 plus A4 cosine theta 1 plus theta 2. Are you with me so far? Same thing happens over here. So this becomes A2 sine theta 1 and this guy becomes A4 sine theta 1 plus theta 2. And that is what is shown here. So no matter what technique you use, so we have solved our first manipulator. This is called as the manipulator. And always remember, no matter how many joints are there, you always take 3 joints at a time. No more than 3, because if you try to do more than 3, the system becomes more, it becomes constrained. So if you have a 6-degree of freedom manipulator, then what you do is you first group first 3 joints and then last 3 joints. Only then you can solve those. If you try to find a general solution for 6-degree of freedom manipulator, that is not possible. So always do with 3 joints. And believe it or not, the next part is, if I take derivative of the x expression, I get velocity of end effector in x direction. If I get the derivative of y, I get the velocity of end effector in y direction. If I take the derivative of z, that is 0, which means the end effector does not have any velocity in the z direction. Everyone understood this? If you are mathematically inclined, you are welcome to take the first derivative. If you want to go a step further, take the second derivative and use Newton's law of force is equal to mass times acceleration, and you are done with robotics. I'm not kidding, I'm serious. But I don't like Newton's laws, because understand, Newton's laws, they are the vector equations. So I have to be mindful of the forces and the moments in positive or negative direction. So I would use something called as energy principles, which actually will give you the equations just like from the expressions that we have derived. Now, what I want to do is, at this point, everyone understood what I did here? Okay. Now I'm going to show you how simple it is to solve this using Matlab. And bear with me, if you have Matlab, this would be a good time to run Matlab. So new script, you can use like, actually, Matlab is so smart nowadays that you can actually write the homogeneous transformation matrices and then connect it to the Simulink animator, and it will actually animate the robot. So you can look it up. And you can do that in the live editor, or you can do it separately. But for the first part, I don't want a live editor. I want new script. So as per Matlab naming convention, a number cannot be the beginning of a variable. So when I write that in Matlab, it will be H01, which means in our case 0H1. Finally, everything is the same. Okay. So SYMS theta, can everyone see all the way in the back? Theta 1, theta 2, and T. Theta 1, actually, let me do it like this. Theta 1, T, theta 2, T. Because I want to do the velocities also with Matlab. H01 is equal to cosine theta 1 T. Actually, I can just say theta 1 minus sine theta 1 0. Then I can do semicolon sine theta 1 . Yeah, I need to add one more term, right? So okay, A2 times cosine theta 1. Hold on a second, hold on a second. I know you guys are smart, so you are welcome to go ahead, just code it in H01, H02, and then multiply those terms. So that should be fine. Okay, sine theta 1. Then,
Minus sine theta 1, you have an extra bracket between theta and 1.
oh, I have a minus, right?
Yeah.
Okay, good. Sine theta 1, cosine theta 1. Now you know how difficult it is for a coding interview, right? Somebody is watching while you are coding. Get used to it. So sine theta 1, cosine theta 1. What else did I miss? There will be 0. Actually, I will do it like this. 0. And so on. Cosine theta 1, 0. Then I will have A2, A2 sine theta 1, sine theta 1. And so on. Then this is 0, 0. There is 1. And then here, there is A1, right? A1. No, it's not A3, not A3, A1. A1. Then semicolon and so on. 0, 0, 1. Oh, 0, yeah. 0, 0, 1. Okay. Now next thing, copy.
Third column, second row, data is.
Yeah. Anything else?
In the copy version to this.
Yes, yes, of course. A4, A4, theta 2. Yes, yes. Understood. Man, you guys love finding mistake, don't you? Okay, 1, 2.
H1 to second row, theta 2.
Yeah, theta 2. Anything else? Yeah, first line.
Second row.
Which column?
Sine theta 1.
Okay. All right. A2 and A3. Oh, A2, A3, A4. Yeah, A1 also, correct. Okay, happy? H02 is equal to H01 multiplied by H12. And this is your forward kinematic solution. You can actually simplify so simplify and you will realize that this is the exact same solution that we have. So this is, now here is something else that I want to show you. A2, A4 cosine theta 1, cosine theta 2, A3, A1. The only part which I want to talk about is how would you find the velocity? To find velocity, so you can say H02, first row, fourth column. Yeah, now it's a symbolic variable. So yeah, so I will show you the way I would do it. It's a symbolic variable, it would complain. So what you will do is basically you will grab this whole thing and use the command diff, and it will give you the velocity in x direction. So copy, and you will say paste. So I would say x is equal to, and this is not, basically you can do it with the same script, but since it's a symbolic computation with an independent variable, that's why you can't directly extract the matrix, but I'll show you how it can be done in just a second. So you copy this. Next time I'm gonna get my mouse. So the command here is just do diff x comma t. And you have the velocity in x direction. This is the Vx. Get evaluated.
So it's come under the variable answer because we haven't assigned left to anything.
What?
We haven't assigned the text to any variable, that's why it's coming under the answer. That last line is.
X is equal to this guy. So this is my first thing, evaluate, right? And then my command is this guy, x diff. Yeah, so this is the answer. The only thing here is, the only thing that you should be aware of is Matlab is showing you this quantity, which is the differentiation of theta 1 t with respect to t is theta 1 dot. and differentiation of theta 2 with respect to t is theta 2 dot. And other than that, you got the velocities of the end effector. So I'm going to stop here. And next class, I would work out few more problems.